Hi everyone, this is Chem Interview. Here we usually talk with the most outstanding people from chemical science and industry, and our today's guest combines both qualities at once. This is Thomas Klapötke, the man who knows nearly everything about energetic materials and all it's used for. Mr. Klapötke, thank you very much for joining us. May I ask you to tell us a few words about your discipline, which is not an ordinary one?
Okay, my good morning to all of you, or good day. My name is Tom Klapötke. I hold the chair of inorganic chemistry here at the LMU, Ludwig-Maximilian University of Munich. And my research area is energetic materials. And under energetic materials, we understand not only explosives, but also explosives, secondary and primary explosives, propellants, and pyrotechnics. So all of my students, of my researchers, from master students up to postdocs and habilitants, they are involved in the research of energetic materials. Mostly experimentally, we see ourselves as what we say synthetic chemists. We use computational methods to supplement our work, but the main emphasis is synthesizing and creating new chemical energetic compounds.
Could you please explain a bit to those who are not really into organic chemistry, and we have a very broad audience, what are these high energy density materials?
These high energy dense materials can either be organic or of inorganic nature. These are metastable compounds. That means the decomposition into products is highly exothermic. However, they are stabilized by a relatively large kinetic barrier. But once you trigger the compound, they will release a tremendous amount of energy and convert into usually gases which are much more stable than the original explosive or energetic material.
But what did inspire you to study precisely energetic materials?
Yeah, that has nothing to do with my childhood or with any experiments I carried out in the garage in my parents' home. I never did anything like that. I studied chemistry, and after my PhD, I wanted to do my habilitation. That was in the late 80s. And naturally, you want to do something new during your habilitation work. And at that time, I also was very interested in quantum chemistry. I wanted to do quantum chemical calculations. Those days, the computers were much more limited than they are now. So the molecules had to be small in order to compute them at a reasonably high level. And new and small, simple molecules which had not been investigated previously, often happen to be either very unstable thermally or explosive. So I decided to look at halogen azides, X and 3, where X could be fluorine, chlorine, bromine, or iodine, synthesize the compounds, characterize them spectroscopically, and also computed their properties. And all these compounds happen to be highly explosive. They never had and still don't have any real application, but this brought me into the area of energetic materials. And after my habilitation, I moved to the UK. I got my first chair in Glasgow in Scotland. And there I started collaborating with the RAF, the Royal Air Force, and other British defense authorities. And that brought me more and more into the area of also applied energetic materials.
Could you please describe the general features of explosive compounds? What exactly makes them explosive, and how can you distinguish those features?
Okay, the features you usually have in an explosive compound, and here I'm talking about what we call ideal explosives, are that you need to have a fuel and an oxidizer. And you would like to combine this in one and the same molecule. One of the most famous and oldest explosive is TNT, trinitrotoluene. So you have a 6-membered carbon ring, that is a fuel, and you stick to this 3 nitro groups, which are the oxidizers. And if you trigger that compound, it will decompose to form carbon monoxide, water, and nitrogen. And the decomposition reaction is highly exothermic, so it releases a lot of energy. The reaction is very fast. It occurs in an ideal case supersonically. That is one of the requirements for explosion or detonation, I should better say. And for this, you need the oxidizer and the fuel combined in the same molecule. You could also mix 2 compounds, but then you never have really an ideal explosive and also not an ideal detonation.
A question regarding the application of this kind of knowledge. You mentioned that you have been doing something for the Defense Ministry. Maybe you could elaborate on it. What was exactly your work there?
Right. Well, our work is to a very, very large extent related to defense technology. We haven't, I wouldn't say we haven't done, but we have done very, very little in the civil area of application of explosives. So we did work in the past, as I mentioned, for the UK Defense Authority. And after my move to Munich in 97, we have always extensively collaborated with the US American defense authorities, as well as with the German armed forces, with the German Bundeswehr.
Yeah, but what exactly was your mission there?
Our mission is we are chemists. We are capable of synthesizing new compounds. And these new compounds should have lower environmental impact, lower toxicity. I can elaborate on all this in more detail. But at the same time, they should also be more powerful. If you try to replace an existing explosive with something that is, say, environmentally more benign, but has only 80% of the performance of the existing explosives, then no one would really buy that and no one would like to use it. So if you want to make the compounds more compatible, less toxic, you also have to look at the performance side and make sure that the energy release, the detonation pressure, the detonation velocity, the heat of detonation are equal, or in ideal case, higher than those of already existing materials.
And what are the strategies towards those environmentally friendly compounds? What makes them environmentally friendly, and what are the main sources of toxicity and harmness for the environment from the usual explosives?
Well, if we look, it's the easiest to explain in the area of primary explosives. The primary explosives, even today, are usually based on lead azide and lead stiffenate. And lead is a heavy metal, which has a high environmental and even greater human toxicity as a heavy metal. So if it was possible to replace the central atom lead with something less toxic, more benign, like iron, zinc, then you would reduce the toxicity of a primary explosive. And that's one area we also work in. Another example would be a typical secondary explosive. The most commonly used one in the military world is RDX, which stands for hexogen. And RDX has a relatively high environmental toxicity. It shows to be teratogenic towards at least one biological species. It's a kidney toxin. And what we try to do is to replace RDX with compounds we call high nitrogen materials. This is a different strategy, to have a secondary explosive which consists of, what do I mean by high? More than 60% nitrogen. So when this compound detonates, it forms to a large extent, not exclusively, hot nitrogen, N2, because N2 is such a stable entity. And needless to say, we also have to look at and investigate the toxicity of our compounds, which we do in collaboration with biologists and toxicologists around the world to make sure that the compounds are less harmful than the presently existing ones.
When you started doing something connected to military goals in your research, was it provoking any kind of controversial feelings in you? If I'm not mistaken, some young people from the German left party, which often opposes NATO, even published a critical article about you. There you're in called a bomb maker. So was it a kind of ethical dilemma for you?
I think here I have to disappoint you, to say no, it doesn't. My philosophy is we are, by we I mean Germany, are part of NATO, and NATO is our home and is our friend. And we either have an army within this treaty, and then I would say it is immoral not to equip our own troops, our own soldiers, with the best available material. And that means the most powerful and also safest material we can offer. The other alternative would be, which I see as an alternative, is to say we are pacifists, we leave NATO, and we hope for the best. But I think history has taught us that this is not a very, very good approach. And like I often use the example, if you send a police officer to a demonstration where protesters throw Molotov cocktails and you arm the police officer with a wooden stick, that would be irresponsible and immoral. And if our enemy has a very powerful weapon systems available, then we have to make sure that our own troops have better material.
Well, thank you for being honest. You have mentioned that one of the remarkable features of high energy density materials is the presence of nitrogen in very high amounts. Recently, as we know, you have succeeded to synthesize one of the most unstable compounds in the world, this C2N14 compound. And in this sense, the question is the following: how do you maintain safety in the lab? How do you work with such dangerous compounds that can become very harmful to people?
It's an interesting question. You mentioned the C2N14. In the recent issue of JACS, the Journal of the American Chemical Society, we published the C2N16 molecule, which consists of two tetrazole rings, which are linked by diazo bridge, and both rings also carry one azido group, which increases the nitrogen content even further. So these compounds, the mentioned C2N14 and also N16, are purely of academic interest because they are so sensitive that no sane person would ever even consider using these materials in any application. But sometimes they are side products and also of interest to us. We are basically more interested in synthesizing new high explosives, which deliver more energy than C2N14 or 16, but are more stable, have a higher barrier of activation barrier, and can be handled relatively safely. You mentioned the question about safety in the lab. We have the general rule: no synthesis of a new material, of a new compound, has ever started on a scale larger than 250 milligrams, not grams, 250 milligrams. We synthesize a new compound, 250 mg, and we look afterwards at the impact, the friction, and the electrostatic sensitivity. And once we have those numbers and interpreted them correctly, we have the rule of 3 in terms of scale up. So the next time we could do the synthesis on a 750 milligram scale. And then we measure all these 3 numbers, impact, traction, and electrostatic sensitivity again. but with higher accuracy. We cannot do it on 250 milligrams. That's why low accuracy, high accuracy. If the compound is still promising and if the sensitivity values are still okay and reasonable, we would scale it up again, usually to about 2.5 grams. Then we again measure those values, but we also measure other data like the hydrolytic stability, the vapor pressure of these compounds. And again, if promising, after the 2.5 grams, we would usually do 5 grams. I know it's only factor 2. After the 5 grams, we would do 10 grams. And only in exceptional cases, if the compound's exceptionally good, promising, we would go beyond the 10-gram synthesis. The largest synthesis we have done is like about 250 grams, not milligrams, grams of a compound. And if you need more, you could repeat the synthesis 4 times in order to synthesize a kilogram. But for every step of scale up, we look at the stability values again. We look at the thermal stability. We look at the vacuum stability. We do DSC, TGA, DTA, all these thermal measurements, isothermal heating, just to guarantee that we know about the stability and therefore about the safety of our compounds.
I want to take a little step back and ask you to give us some good examples of recent breakthroughs, inventions, which would be well suitable for presenting the fields of studying explosive materials and energetic materials.
Sure. I could mention one of our discoveries about just over 10 years ago. We, for the first time, synthesized and published the compound, which is now known under the acronym TKX50. And TKX50 is a new secondary explosive, which has a detonation velocity higher than that of hexogen, which is a most commonly used military explosive. But equally important, its impact sensitivity is much lower. For example, hexogen has an impact sensitivity of 7 joules. You have to knock it with 7 joules to make it explode. For TKX50, you need 20 joules. So it's almost 3 times as much energy you need to set it off. But once you have set it off, the detonation performance is superior to that of hexogen. So it is more powerful, but safer. And that is very difficult to achieve because it's not difficult to make something which is more powerful, but often then it's also more sensitive and less safe to handle. And this material we first published 10 years ago, and it has been patented, has been scaled up, and is presently under investigation for new formulations, like mixtures of compounds with a large European explosive manufacturer.
We have discussed the explosives, but it's not the only area of your active research, and the next one is the fuels and the materials. The modern types of fuels are rather non-environmentally friendly, like oil or gas. But there are some ideas to use some mixtures in such a way that the combustion products will be more safe than they are nowadays. So what do you think? Is it possible to invent some fuels in the near future that will be more environmentally friendly and also economically feasible?
Yeah, rocket fuels are particularly nasty in terms of toxicity. Usually you have to have a fuel and an oxidizer because a rocket flies at relatively high altitude. It's not an air-breathing engine. It cannot suck in oxygen from the surrounding air. You need an oxidizer. And the only oxidizers really used on large scale in storable propellants are either red fuming nitric acid or N2O4, the dimer of nitrogen dioxide. That both have severe corrosion and also toxicity problems. The fuels themselves that are in use are usually based on hydrogen and its derivatives, like methyl hydrogen or dimethyl hydrogen, which are toxic and which are all carcinogenic. And there is a large room of improvement. Especially in the area of oxidizers, there is hope that the red fuming nitric acid and N2O4 can be replaced by 100%, more than 99% hydrogen peroxide, which would make it much, much less toxic and also environmentally benign. Whereas the hydrogen derivatives could be replaced, excuse me, the hydrogen derivatives could be replaced possibly by hydrocarbons like methane or higher hydrocarbons. That is perhaps not the final answer, but in medium intermediate terms, that would be already a great advantage. In the area of solid propellants, the only oxidizer that is used is ammonium perchlorate, at least in the Western world. And perchlorates are also toxic. And here it's much, much more difficult to replace the ClO4 minus anion with another oxidizer. There is hope. There are some candidates on the list, but that doesn't come for free. So you have to invest quite a bit of money in terms of research. And you also have to be willing to pay more for the rocket fuel than for the relatively inexpensive perchlorate. But both are possible. Another area would be ionic liquids as fuels, because most rocket fuels have a relatively high inhalation toxicity, and an ionic liquid, though it's liquid, has a relatively low vapor pressure. So even if it was toxic, the risk by intoxication by inhalation would be relatively low. And these are areas where people presently do research on, including ourselves. I know that is not the final answer, but in the foreseeable future, I do not think that there is a way to avoid chemical propulsion. You could think about nuclear propulsion, which is also, for political and other reasons, not so welcome. And so I think in the years to come, in the decades to come, we probably rely on chemicals and have to make them safer and better for the future.